from Atria University. It's a pleasure to be here for the first time. So I actually, so let me tell you a few things. My administration load is so high. I started my presentation post 10:30 p.m. last night. So I was actually wondering, I in fact asked once, woman, should I actually give you the title of the lecture? That would have been a much better choice. He said, you just keep it open, sir. You say whatever you want. So this is typically, yeah, okay. Thank you. So what I'm going to talk about is probably more India specific. That's why I've chosen this title. And what I'm going to tell you first is, what we actually do and the way we have conducted research on energy storage systems at the Institute of Science. I actually joined the Institute of Science just with a polymer background. I never did anodes, no cathode, no separator, no batteries. It's just soft matter. Okay, and it's only at North America at Max Planck, he told me, look, you need some applications. So that's the time we started lithium ion. That was quite a way back in 2002. Alright, so back in India, of course, that was 2006. So typically, what are we looking at? Of course, now it's widely recognized that energy storage via rechargeable batteries is one of the lead options. There are other options as well, but what it has done is, at least the time when I came back, it was already a success story in portable devices, right? And slowly things moved on. Electric vehicles, with a lot of AI coming in, I believe storage, battery storage will be available. We will be going into data centers, strategic applications, and space, because ICER looks for space-grade batteries. I never knew what a space-grade battery is. Alright, so all this, the entire game is in the hand of lithium-ion batteries right now. Aninda gave a very nice introduction into it. I don't really have to go into explaining an electrochemical potentials of cathodes and anodes. So, lithium-ion is the champion. We have industry people here that are also doing lithium-ion. But what has happened is, it's over half a century of lithium-ion already. So, we are now seeing the fruits of lithium-ion transcending smaller devices. But what has happened is, because of the advancements in understanding of materials, how you make them, or mechanisms, how you manufacture them, and we've been lucky, that the cost of lithium has also come down. So with this kind of attempt, it's not that we are inventing all these things. Actually, the story of lithium started with lithium metal. We are going back to lithium metal because it has certain properties in terms of storage. Now, when we talk about lithium metal, of course, involved with this is we are talking about as well. Yes, a lot of old solid state system is also going to come up. Okay. Now, and then of course, there are a lot of sustainability drives across various companies. And you have to make things cheaper, they have to be safer, they have to be scalable, and it should not harm the environment. So, in this scenario, there is also again a nomenclature which is very much used in the energy storage domain post lithium. But if you actually look at any of these systems, they were even before lithium-ion. Lithium just picked up because you can't beat the physical properties of lithium. It's just too good. So these systems are expected to be, because they're more earth abundant, as given here in the sodium, potassium, or some of the higher level systems. They're supposed to be more cost effective, safer. I'm not really sure, because when I tell my student to do some experiments in sodium, she says, sir, what I did with lithium, I think I will not do with sodium. It's a very dangerous, especially if there are students. It's not even more dangerous than lithium. So these have come up, but so because of the cost and abundance and a much more stable supply line, the safety or whatever non-trivialities coming your way, that is pretty much offset by these economies. So we're still kind of operating in the uncertain way, but we try to have other examples coming up, which may not see the light of day immediately. These are where you're using a conversion cathode, where you are actually using a chemical reaction to store, right? And and the examples are sulfur or oxygen. At least theoretically, oxygen is the one which comes closest to the ICE, but you have to wait long because it's very difficult to have a clean car in a breathing mode all the time, okay? And especially when you have to carry a lot of oxygen. So under this domain, there is also very promising systems, flow batteries. We also do a little bit of flow batteries, not the vanadium redox or organic systems, but more to do with polysulfide flow batteries. Now, the question is, there's a lot of options. You can work on the options. Well, what exactly, what are all these going to do? It's very difficult to remove lithium because the energy density of lithium is very high. It's very difficult to have anything close to lithium, at least in the time being. But so what these systems are able to do is kind of supplement the lithium. Places like India, I think, is better to stick to sodium or much more earth-abundant elements, right? So in places like India, of course, we have some lithium-ion manufacturing going on, but I think better to pick a system which is suitable for medium conditions. But again, having said this, someone told me, sodium, a lot of work is going on in sodium. It's still 5 to 6 years from the time, so it's half a decade. So probably we'll have to work with supplementing lithium-ion, but they do provide complete energy storage solutions. But again, in this domain, we have a lot of competitors. Hydrogen, 300 kilogram car can be, if you have the right combination of materials and the device, that can be replaced easily by a 5 kilogram operated based on hydrogen. Okay, so there are competing technologies. Okay, so what are the R&D research processes? Of course, whatever I have shown, we work on several of these fronts. But I think the way to go ahead in the next 10 years, we have identified a few fronts, both from based on materials, mechanisms, scale up, and so one of them, of course, is I think what Maria said a little while ago on solid state, right? So the way we envisage solid state is slightly different from what she has described. Actually, I will go to the laser pointer here because somehow I'm a bit tentative with this one. Let's see. Now this is yeah, okay. Yeah. So this is one of the fronts where we'll be working. Secondly, the second important point is what we would like to do is work on sulfur-based systems, and I'll quickly tell you what these are. And the final thing is, which has become very important with time, are the aqueous batteries. Okay, if you can make an aqueous battery work, that's going to be wonderful, because then half of your investment, can reduce half the investment, because you spend a lot of money in having a pristine environment in making lithium and sodium or any of the non-aqueous systems. And there are, of course, certain other things which is not really based on electrochemistry, but which needs a lot of engineering input, because I'm now in an interdisciplinary department. I work with mechanical engineers, things like battery thermal management, the operando diagnostics. Now, this is not just doing an in situ spectroscopy or something, but this is actually gaining knowledge from various sources and building up models at the cell stack level. Pretty much electrochemistry at the stack level. And what is important is something very important for India, trying out feasibility studies, looking at techno-commercial investigations. So of course, in this lecture, because of paucity time, I will only focus on the top three here. And what I'm actually going to share with you some of our endeavors based on the first three platforms, where we do a lot of fundamental studies, but of late, we are trying to scale it up, and that is where national agencies and private industries come into play. And of course, we do, of course, most of our funding though comes from the government of India, but of late, we are trying to attract funds from various other agencies. Okay, so as I said, lithium-ion is important. There is a shift from lithium-ion to a lithium metal-based system because of the energy gravity and safety concerns. And the other thing is, we want to have no liquids, just to have a full solid state system. And this has been shown very easily. If you actually take, compare the state of the art cathode materials for lithium ion, like the NCA or the NCM, LMO, the moment you switch from the liquid to a solid state system, you actually gain quite significant amount in terms of specific energy and energy density. And I don't know, of course, we see a lot on YouTube and Google and all, they say, this is going to be a reality in 2028 and 2030. Well, I don't know. This it depends on for whom you work, or which is the company who is publicizing all this. But I think it's going to be quite a challenge to have solid state system mass scale. That is the important. If you have some niche application for solid state, that's a different thing. But if you really want to make your devices lighter, mobile phones lighter, that's a tall order. Okay, now the way it has been depicted that solid state will be through solid inorganic electrolytes. Now, to me, none of these compounds are new. They've been there since early 50s, 60s. These compounds have been hanging around. They are in market. Then people try out, things don't work. They completely go undercover. And now again, it has come back. So that's one of the way of going through. But looking at the strength of our lab, we have been actually working on soft matter systems. These are so-called solid-like systems. Okay, they are the conductivities are lower than that of a liquid electrolyte, but the mechanical properties are better than that of a liquid electrolyte, but not as great as a solid system. That is where typically the electrolytes lie. And why we, of course, examples of soft matter are polymers or viscous liquids. And why we are interested in them, because the diversity these systems can provide in terms of composition. You can play with the macromolecular structure, and the most important thing, which is a big drawback with solid electrolytes, inorganic solid electrolytes, is the processability. Very severe restrictions on the processability when it comes into implementing into a device. That's the big problem. So as I said, we have been working on these systems for quite some time. So now, by solid polymer electrolytes, I'm not really referring to these kind of systems which were there for a very long time. The so-called solid polymer electrolytes, where you have a very high molecular weight system, polymer system, and the ion of interest, which is lithium or sodium, it is basically tacked to the polymer. Okay, only if there is a significant amount of mobility in the polymer will you get a suitable amount of a significant amount of conductivity. And most of these designs early on in the 80s or early 90s, they used to work well if you are very close to the molecular weight, to the melting point of the polymer. Okay, and these are very strong aging problems. With time, the membrane disintegrates. You have problems, mechanical failure and all. So the polymeric systems that we are actually interested, these are more cross-link systems. So it's so you generate these kind of cross-links either chemically or physically, and you have trapped liquids in this empty zone. Okay, so you have the strength of the polymer as well as the mobility which of the confined liquid inside the polymer matrix. There are, of course, various versions of it. We mostly stick to somewhere in between a simple network and a semi interpenetrating network. Alright, so these are some of the earlier designs. Now, let me tell you, whatever design I'm going to show, you can scale them up, you can make very good films, and that's actually what a battery company needs. So they have these huge roll-to-roll coaters. They first make the electrode, and of course, and then if they're using liquid electrolyte, right, it goes to a liquid electrolyte filling machine. That's how the thing works. Now, if you have a solid electrolyte in this, that's a huge investment in terms of changing the assembly line. Okay, so the advantage of these systems it's the same roll-to-roll coater after the coating of the electrode. That can be put into this. It can be rolled down to this, and then of course you take it through a simple heat treatment or some other protocols. Okay, so these were some of the early systems that we planned. You actually make a cross-link system, your liquid is trapped inside. It could be a solvent, molecular solvent liquid, or it could be a room temperature ionic liquid. The earlier designs, what we are focusing on, how the ion, let's say the lithium or sodium, can be decoupled from the room temperature ionic liquid. Okay, so that the dynamics, it goes into that older picture. So the dynamics of the ion in the system is still controlled by the polymer. Okay, so these were, of course, you can run batteries, but the problem comes when you actually want to scale it up. So, we are academic labs. We're always at the points of 2032, but I think over the last 5-6 years, we are actually scaling up to power cells of various sizes. So that's actually where you will see your science published in JACS or wherever is falling short. It's just not missing the mark. It's just nowhere. Okay, so there you really have to work on designs which will actually give you a practical set. And these are things which we've been doing for the last few years. And this is an example. Again, very careful design goes in. So you have a component, which can very easily solvate an ion, but then too strong a solvation will not give you a good conductivity. So what you do is, I think, you use succinyl nitride. So we use similar molecules to plasticize it. So you actually render dynamics. You actually move the lithium or sodium much faster. Okay, so this is the polymer component which will give you the scaffold, but you also need the liquid electrolyte where you need the conductivity. So when you put this in a bottle like this, you do the polymerization reaction, you get very nice films, and of course we have done this over the last decade or so. We're getting all these papers on very high concentrated liquid electrolytes. So you can actually also make these polymers with very strong, very high concentrations of polymers of the salts. Okay, so what we are trying to solve here is, these are really compact structures. Okay, as you see, this is a compact membrane which makes a very good, contact with the electrode, and you run it for several thousand cycles. The liquid electrolyte is failing because you start getting dendrites, but here you actually don't see any dendrites. Okay, and then this is sort of lithium example which we did, and here are some of the properties. You can actually plate strip lithium for several hours at various current densities. Okay, a slight modification we did. This is for more applicable to sodium, but we can also do the lithium. Is that instead of just generating freestanding films, why don't we actually polymerize directly onto the cathode or the anode? And as you see, we're getting very good thickness. These are the kind of cell guard, polymer membrane, thickness that you get. They're very stable, and you can of course plate strip for very long hours. And the most interesting thing is that you can run it with various types of sodium battery electrodes. And of course, the one that I'm going to show you is this is with MVP. You can run for 500 cycles. It's very interesting. This polymer is stable in both zones of the NZ. So you can make the polymer work with the V3, the vanadium 3+2+ redox couple. You can also make it work with the 4+2 3+ redox. So these are half cells. You can actually also make the full cells, and you can have a pretty good battery running for 1,000 cycles. So these are pouch cell data, which I'm actually showing here. All right. So I'll actually quickly tell you, because there is a paucity of time. So what is the summary and outlook? We keep on working with polymers. Of course, it provides you much more free hand if you really want to have a solid state cell, right? With things like gels or viscous liquids and so on. I'm not showing the viscous liquids, but even with viscous liquids, these are very stable. But the challenging part is that you have to match the conductivities of a good solid electrolyte, right? Of course, you cannot match the conductivity of a liquid electrolyte, but at least it should be as close as or better than a liquid electrolyte. Very demanding in terms of the shear modulus, and that's mechanical strength, and so it is quite demanding. So one of the ways, of course, you can still go ahead with newer polymer systems, but that takes again may take a half a century. Okay, and I don't think so. I have the time to wait till that period, because so the other way would be, which is something which many in this field are doing, is actually to build systems where you have an inorganic component as a filler. All right. Now, in this domain, I'm not really referring to, these are old style of work where you have a polymer and you have less than 10% of fillers. So what this is doing is not really altering the effective conductivity of the system. So the conductivity is still quite low compared to, let's say, liquid electrolytes or even solid electrolytes. Why? Because no, these are not fillers, insulating fillers. This is maybe a solid electrolyte itself, a ceramic solid electrolyte. So the problem in this kind of loading is that you still don't achieve a great mechanical strength. And the problem is your conductivity and your electrical performance is not going to change much. And we have earlier on we have done this kind of work, where you actually take these kind of insulating particles, organically modify it, and we have done a whole host of things, not only batteries but also in dye-sensitized solar cells. But what we are actually looking at now with designing is the filler content should be the majority fraction. Okay, so in this way, what the polymer does is kind of a binding element, or kind of a binding conduit between the various solid electrolyte particles, which is going to give you a conductivity matching that of a solid electrolyte, but with much better adhesivity and much better interface, which will lead you to a high-performing battery system. Okay, now coming to the next topic, this is the ones where you're doing conversion chemistry to store energy in a battery. So now the sulfur batteries based on lithium, sodium, magnesium. There are lots of examples. They've been around. The best is of course lithium because of the energy density. So quickly, just for the students, why we choose sulfur? Of course, sulfur is cheap. You can just get it from anywhere, right? The energy densities are probably theoretically at least better than the best of the intercalation cathodes, and it's low cost. Someone said that if you really want to design a dirt cheap technology, do it from dirt. So sulfur is really cheap. It's dirt cheap compared to, let's say, a cobalt, a kilo of cobalt, or a kilo of nickel. All right. So the way the conventional metal sulfur battery works is because sulfur is very good in storage, but it's a very poor conducting system, neither electronically or ionically. So it is always housed inside a host. Most of the time it is carbon. Okay, and it is separated from the metal anode, in this case lithium, by a liquid electron. Now, since this is not an S2 or an S system, this is an SA, the puckered ring of sulfur. It's not a direct conversion. Okay, so when you're discharging the battery, it passes through all these steps. Okay, so you have these higher order polysulfides, lower, and finally you form, if at all the kinetics is favorable, you will form metal sulfide. So it's actually may appear to be a very simple cell giving high energy, but the operation of the cell is quite complex. And then when it discharges back, to SA. So as you see, this is a multi-step, and the major problem of the sulfur system is this redox shuffle. Okay, so if it dissolves out of the cathode, it has a tendency to diffuse towards the anode side, and it starts poisoning the anode. It forms the end product on the anode side. So you have a problem of loss of sulfur, you have a problem of capacity fade just from this. And since you are using directly lithium, just like in lithium ion, you have this dendrite issues, which is a key issue. Now, again, depending on the dominant ion, lithium, if it is lithium, if it converts from sulfur to Li2S, there's a huge volume expansion. It's about 80%. If you take sodium, it could be 300%. So these are the two major issues. But since we have been working on this for almost now a decade, we have found out other problems. There is a change in the state of sulfur, which many don't even know. You start with sulfur in the crystalline state, but if you just keep this in air mixed with some high porosity carbon, it changes completely to an amorphous state. So that shows a very different kind of form of cycling. Very interesting investigations we had with reaction kinetics and so on. Okay, so what could be the strategies here? Of course, we have worked on several fronts. One is you should have a very good sulfur cathode which can have a very high loading, and most important is the utility percentage. And you can load 90% sulfur into a cathode, but the utility is only 10%. Then that will give you a very poor capacity. Okay, And it should be on-site trapping of the polysulfide. All right. Look at alternative electrolytes. There have been strategies. Why work with a lithium metal? Why not work with something which can lithiate it, or which can insert lithium and so on. So these are some of the strategies one looks at. So when we started a while ago, just like everyone, we adopted a conventional strategy, right? Design very good porous hosts so that you can trap a lot of sulfur in it. And so, if you can trap about 70-80% sulfur in the matrix, then you can probably end up with a very high capacity battery. So these are some of the early examples. I think most of our learning was done in the first paper, where I used to keep on telling the student, look, your loading is only 70%. Why don't you load 100%? So the problem is, you load 100%, all my tubes just crash out. So you can always get a very poor battery. Okay, so starting from multi-wall carbon nanotubes, we learned how high you should load. Second, when we move to a very simple system like zeolite, you can get it anywhere. Zeolite has two different kinds of cores. Depending on where the sulfur is, sulfur has very strong confinement effects. So we have seen this kind of diradical formation, completely unfurling of the sulfur if the core size is bigger, or if there are less coordinating units. So these are some of the things. And then, of course, this is a very nice system. You're actually using polymer to wrap the sulfur, and that does all the entrapment of the polysulfur. But then, making even more complex systems like the covalent organic framework, we started to learn that the trapping of sulfur, depends on which is your coordinating functioning group, right? So it can be that the lithium from the polysulfide can be trapped on the surface, okay, on the host, or it could be just, if you have something else, you can have a sulfur of the polysulfide getting trapped to the host. So the trapping mechanisms are also very unique. Okay, so the motto of this is, of course, you can design good hosts, you can publish well, but the cathode volume expansion still remains, and we have completely no clue on the mechanism of the trapping in these systems, right? And even if you, in this very high porosity host, if you want to introduce an electrocatalyst, the role of the electrocatalyst is completely unknown. So we have to kind of slightly change, because, and this was around the time also, we thought that this is a system where we can do some kind of real applied work, some scale-ups we can do, because we have a lot of expertise in making materials. So we kind of looked at simpler configurations. These are more kind of in tune with what an industry would prefer, right? So, getting a high porosity host, industry has to really think how to infiltrate 2 kilos of sulfur into. If you look at the reactor design, that will be really huge reactors and energy consuming. So what we did was just invoke something, I think, which Mustafa does, invoking the concept of electrocatalyst, right, into the cathode of the sulfur cathode. So you make your sulfur cathode much simpler. Just mix things like carbon black, very simple as Kedgen black, mixed with suitable amount of sulfur, and then you have a suitable amount of additive, which is an electrocatalyst. Okay, so this was one of our very early work. Again, it works extremely well, but it's only a paper, right? You have cobalt, nickel. It's a great battery. At room temperature, you get good capacities, and even at 1C rates, you can actually also make a sodium sulfur battery with this. The cobalt nickel sulfide, the way it works is it is actually the sulfur of the polysulfide, which is because of some residual charge, gets kind of helped by the cobalt and nickel. Okay, so this is the whole thing is it's a kind of proof of concept that you can actually use electrocatalyst working in a sulfur and doing the trapping and conversion mechanism. This is something which around this time Professor Mantiram had a lot of papers on using interlayers, but they were all based on carbon. So what we did was, right, we did not take carbon, we took nickel oxide. All right, this does the same thing. Now, what we are doing here is, instead of having everything on the sulfur cathode, you kind of shift the center of action from the sulfur cathode to an interlayer, which is basically a separator with the nickel oxide coated. Okay, so this does a wonderful, electrocatalytic reduction of sulfur to lithium polysulfide, lithium sulfide, and back. Okay, and the important thing is, you get loadings which are pretty high. You can go as high as 10 milligram per square centimeter loading in these kind of systems. So we always, of course, so the advantage here is you now actually have some hold on the reaction. You can make out, you can do a lot of in situ or ex situ studies to figure out where what is happening. And the most important thing is you can actually mitigate the volume changes very simply by using these kind of strategies. Now there have been other strategies which are not really some additional steps get added. Is that why start with sulfur? Why not with the end product of the reaction like the lithium sulfide? So what you immediately do is that you mitigate this volume change which takes place because of the conversion of sulfur to lithium sulfur. Okay, so you start with this. The only problem is if you don't have a good clean room, lithium sulfur is very hygroscopic. Okay, so you need a clean room. So that's why the students have to always make cells inside a glass box. Okay, so the other problem is now you're going from sulfur to an ionic compound. So you have this problem of an activation barrier. Now this is something I must tell you is not our idea. It's actually proposed by IISc lab from Stanford. Okay, this, as you see, it was quite a while back. Of course, this picture is not from that paper that proposed sometime in 2011, 2012. It's because of this activation. There is a technical problem if you actually want to make a practical cell. So you have to design electrocatalysts which can bring down this activation barrier, and this is what we have been successful. And the next slide is, of course, I won't be talking much in terms of what we did because this is all under patent and protection. So we did a whole host of things. We have designed here electrocatalysts. Okay, I must say here, I don't know, we don't have that many young students, but this is just using NCERT class 12 chemistry, right? The electrocatalysts are designed here. We can actually scale it up in the lab. So what these electrocatalysts do, if you add in optimal amounts to sulfur, or let's say the end product of the sulfur lithium sulfide reaction mixed with biomass derived carbon, this is also something which we are actively looking into because you need carbon in sulfur, and the carbon has to be from a cheaper source. So what this does is firstly, of course, you generate a very scalable composite sulfur cathode plus an electrolyte in electrocatalyst. And we again invoke the concept of interlayers here. I'm not actually much going to talk about because most of our work right now for the pouch cells has been with lithium metal. But we plan to kind of shift it to something on a lithium coated on copper carbon collector. The problem is importing. We have to import this product from the United States. That's a huge amount of money. But that is something which and we're using actually water-based binding. So what we get is right now in the lab, we can make these kind of single layer cells, these kind of specs. Okay, but the multi-layer is something which we are now planning to do with a national organization and scaling up to a larger size pouch cell, something like 210 by 150, which is typically an A5 size notebook, which is probably distributed in your registration kit. Now the problem that I want to tell you is the publications are very different. You do something random and you get some good results. You're really not bothered about too many parameters, right? When we are actually doing this, we discovered several other parameters. Two of the most important thing is when you actually want to make a bigger size pouch cell, something bigger than a coin cell at a pouch cell level, you have to really start worrying about your rate ratios of the negative to the positive electron. You have to actually worry about how much of electrolyte loading is there with respect to the sulfur and so on. Okay, so these are parameters which you will not see in papers. Very difficult. Even if it is there, it probably is hidden somewhere in the electronic supplementary information. You will never be able to recover all those. So these are the things which we worked on. Actually, we made some projection studies, right? So if you load less of electrolyte, your capacities may be very high. But then these are projections at roughly about 3 to 5 milligram per square centimeter. But the industry, I think, wants more than this, right? Close to about 10. Now, 10 means a thicker electrode. I don't think so your batteries are going to work at such low loadings. Capacities may be high. This is all good for small cells. But so you essentially have to kind of look at numbers around this, which will give you a reasonable capacity. Okay, so now moving on to the last segment, which we feel might be very important for India, is aqueous batteries. And I'm going to talk about zinc here. Now, of course, aqueous batteries, as the name suggests, you just run on water. You don't really need a class 10 clean room or a class 100 clean room, nothing of that sort. Your assembly is completely in air. Okay, so you actually save a lot of money on the assembly line. And the most important thing is, you have a better choice also. Apart from cations, you can have an anion guided batteries as well. Okay, and what is important is that they have been around for quite some time. Nickel iron, lead acid, all aqueous-based systems. But there have been a rejuvenation of interest in aqueous batteries because we need grid storage also. And grid storage, generally, the way things are moving, I believe you have to put this in a remote location. All that the man has to do is, all the person has to do, or the maintenance person has to do, is maybe add some water to adjust the pH and things like that. Right? There's a very almost low maintenance batteries. Okay, now we talked about we took zinc because we work on other. Zinc is very historical. Right? It has been there since the Volta fire. We teach our children, Daniel cell and the Plancher cell and so on. So it is very historical. It has been there. It has a rich battery history. Of course, it fell out with the advent of very smart, very highly efficient rechargeable batteries. But it is again actually making a comeback because of its cost factor and natural abundance. Now, some kind of always get some slogans. So it could be a potential game changer if we do well in aqueous zinc. Okay, so but the problem with aqueous is again this voltage. The voltage separation when you are in the HER is just 1.23 volts. Okay, so that's a low voltage battery. People are going to laugh if you compare this with lithium. But so what are these associated problems? The problems are because this is pure water. We try to tend to work on acidic or the alkaline end, just to increase the voltage range. But then you end up with a whole host of other problems like water splitting, side reactions, corrosion, dendrite formation. And the fun part is we have chosen zinc, but zinc is one which actually like in a non-aqueous system, if you have a new cathode, lithium cathode or a sodium cathode, you can quickly check against sodium in a non-aqueous system. In an aqueous, it is impossible, except zinc. It is troublesome, but if you put calcium, aluminum directly in water, you are done. Your battery is over. But zinc gives you that kind of an advantage. Okay, so you have to somehow deal with the all these problems, and so the whole the game here is how you can generate a higher output potential. So there are strategies based on over potential control or on electrode design, where you can play with the state of the electrolyte, you can play with the concentration of the electrolyte, even have various other strategies. Okay, so as I said, we have various as we also work on aluminum and calcium. We have very similar issues with aluminum and calcium. The other problem with the aqueous is that you're actually dealing with large hydrated ions. Okay, as you can see, if you take zinc, the cation radius is 0.74, but the hydration radius is more than an order higher. Okay, so there are severe problems. So if you have now, let's say, an electrode where the interlayer spacing is double that, even then you would end up with problems because it's a huge hydration drag which the ion takes into the cell during insertion and reinsertion. Okay, so again, I'll be very brief. We are looking at various aspects of zinc. So this is an example. I'll quickly roll through. This is where we have achieved some level of success. Is you modify the zinc suitably. Okay, you protect the zinc, and then of course, you instead of taking an inorganic cathode, you have taken an organic system. And what you see is, of course, these are the comparisons. This is the classic zinc-ion battery with manganese oxide, but we are actually trying, already in the game with these kind of modifications. But again, as I said, these are tough systems to get a working system very quickly. So you have fundamental challenges, right? You have an organic system, it has 2 or 3 various modes of storage of zinc. You can insert it, interlayers. If it is a layered system, you can also, have apart from a coordination plus an interconnection system. And then, of course, you have problems with capacity failure. As you see, we start with very nice structures. Over 400, all sorts of things are starting to happen. So this is something, of course, we have a working battery. So this is actually manipulating the electrodes, the cathode and the anode. One can actually tweak the electrolyte as well. Okay, so let us say you start with a very classic zinc coordination of hexa aqua in the bulk. Okay, with some additives, again depending on the counter anion. All right, you can tweak the hydration in such a way. So we have an additive here. Okay, so in one particular type of anion, which is, let's say, chlorine, you'll have a hydration shell like this, or if you are moved to a sulfate, you'll have a hydration shell where now the additives are actually coming into the play. All right. So what are the advantages? The advantage is you need to get rid of the dendrites. And the important thing is about all these, which is also seen in the non-aqueous counterparts, the multivalent systems, they form large number of these intermediate compounds. So these kind of tweaking, very simple tweaking of the electrolyte composition, you can also get rid of the byproducts. So you have a very clean system of working with a zinc ion. All right. So yeah, of course, we also have to look at the future. So we do work on these kind of metal gas systems. These are very interesting because they are much more open systems. Like half of it is a fuller cell. And why they are important? Because the capacities are much higher compared to the rest of the lithium. So we work on. So what we do here is mostly work on electrocatalysis. Okay? Trying to design electrocatalysts. For example, in the oxygen, this was done at least 2 years back, where we did an exhaustive study of the first two transition metal phthalocyanines. So the idea here is using all these oxygen cells, they are using solid electrocatalysts, which are sitting on the gas diffusion layer. So what happens is, as you discharge the battery, firstly there is a problem with oxygen or any gas diffusion through the layer. But what happens is, because of the irreversibility of the reaction, you start blocking the pores. Okay, so that's a big problem to carry on with electrochemistry. So what we have done is we have taken redox mediators. This is again, this is a concept which many use in electrochemistry. So the advantage of redox mediator is you're not actually loading onto the cathode gas diffusion layer. It is somewhere very close to the electrode-electrolyte interface. So all your reduction oxidation is done via the redox mediator, which is in the liquid electrolyte. So this was an exhaustive study. We looked at how the D shell configuration affects the electrochemistry. In recent times, student who submitted thesis, he actually again designed a bifunctional electrocatalyst. He's now proving the role of defects here. How defects assist a bifunctionality and can generate a zinc-air battery. All right, so very quickly, again, we move to CO2, lithium CO2 batteries. The most important thing is, of course, it's a battery, it's an energy storage. The important thing is, unlike a CO2 electrolysis, where you really have to hunt where your C2 or C4 chain organic compound is, this is a direct solid state product. Okay, you generate lithium carbonate, which is a precursor for any chemical compound, which is almost any compound which is used in lithium-ion battery. So we again looked here at solid state electrocatalyst, okay, in the form of Maxine, and then we used very simple chemical compound like the cupric chloride, okay, as a redox mediator, which gives very efficient batteries in CO2. And the important thing is this, again, as I said, is an example of carbon capture. You do pretty much the same thing. And then here in nitrogen, you make lithium nitride reversibly. And you can also get a reversible battery. Of course, the way to discharge these batteries is if you really want to get something good out of it, you have to not only control the current, but also the constant capacity at which you discharge it. Okay, I think I will end here. This is a very recent example where you are using a zinc-air platform. Okay, instead of going to a 4-electron, right, straight 4-electron, You stop it at 2 electrons, you start generating hydrogen peroxide. Okay, and hydrogen peroxide can be used to treat water pollutants. You can do it in the battery, you can do it in a photoelectric cell, and so on. Okay, so just coming to the summary and perspective, as I said, this slide I started preparing around post 10:30. But before that, I was submitting reports to various offices. So they will be random. So please bear me from my randomized thoughts. So one thing, of course, I know batteries will be a top choice. Various energy storage options, small or big, maybe standalone, maybe in conjunction. That's how things will work. But you will see a lot of competition from various other forms of energy storage. I'm telling you, the government of India is really, it's putting a lot of money on hydrogen, green hydrogen. Okay, so and those guys always tell me, look, man, your battery is 400 kilograms in a car. If my things work, you're out of the game. It is just 5 to 10 kilograms. Okay, so and the thing is, we have a lot of engineers working on that side. They can engineer anything, which I believe as a chemist or a physicist, it will be very difficult unless you tag hands with them. Okay? So the other thing is the speed of transition from fossil fuels. This actually depends not only on geopolitical issues, but every now and then I see one person making a statement, on human ambition also. Okay? So never, please don't fall trap to such things. Now, the thing is, if someone says, we are making solid state cells, doesn't mean India has to take solid state cells. It's very expensive for India. We can look for some other solutions. So we have to choose, very careful about of the battery chemistry, the utility sector of batteries, scalability, cost, supply chain. I'm telling you, when I joined University of Science in 2005, right, I used to give talks on lithium-ion. Okay, everyone is saying he's a bigger guy, all useless. Absolute useless, right? And with this attitude, we actually lost the race for lithium. I mean, if we had realized early on, I think we would have a much better manufacturing-based ecosystem right now, right? Which did not happen 15, 20 years ago. So the timing is very important. Okay, now, of course, there is a roadmap for India for electric vehicles, how you connect low voltage, mid voltage with solar cells, rooftop solar and so on. So what we definitely feel is that EV will definitely make a big impact for Indian city environment. Okay, and definitely for grid off-grid applications, definitely the locations that we're looking at, these are remote, will improve the quality of life there. But again, India presents unique scenario. We were having a chat on the traffic. Okay, so the challenges in India are unique. So I don't know, if you see a Tesla in the United States, in the Tesla in the UK and Europe, already there's a huge change. By the time it comes to Hong Kong, the huge change, I don't know what will happen in India, because I think the AI will become too much for the AI to handle, the driver's mind and all, which is very chaotic in India. So the most important is, as I said, is related to, we should have actually a national program, self-driven national program, not what others are telling, right? So that's why I showed 3 examples here where I believe India can contribute. One is sodium ion, which I did not touch upon much, okay? But again, the infrastructure has to come very fast, because sodium ion, many people say India can be in the game, but where is the infrastructure to actually build deep cells, which China has? All right, so it should be a self-driven, national program, and investments and focus should focus on newer or alternate chemistries which can mitigate this external control on materials and processes and lower down imports. This is something which I feel strongly. You should have a well-defined national program. Otherwise, it will be just like this lithium-ion game. You're buying A, B, C, getting a Z, which is already there, right? And you're just benchmarking where is a Z, which is somewhere else. So yes, this is a new ecosystem. So it's really climate change, right? Many people are talking about gigafactories and all, but I don't know what will be the fallout of those gigafactories on the environment. I was IISc, we get a lot of visitors. So we had a full strength visit from Nordic countries, Norway, Denmark, Sweden. The electric vehicle number is stupendously high in these countries. They're already thinking in terms of, can we have good recyclability? That is something, and circular processes. These are very, very tough questions one has to ask. I mean, you're talking of climate change, mitigating climate change through electrification can lead to some other problems. So one has to be very careful and keep factors like recyclability and thinking about recycler processes. Okay, thank you. I think I'm not too sure how well I went with the time.
Questionnaire, I think so. We'll have during the tea time. Yeah, please.
I have long been between sorry to I think that you were mentioning something about the Atria cathode. It is something like a rechargeable anode. I like the someone who stated that 2005 people are not very happy with lithium.
We started at the same time.
Yes. Something I tell you during the meeting.
So I was in a conference and there was a presenter that presented a safety study. And none of the organic polymers actually were safe. Only the inorganic could be considered safe.
Yeah, again, one has to look at the developmental chronology of these inorganic systems. People spend a lot of time on inorganic systems. And the problem I tell you, since I work with some national organizations who actually do it sell, I really don't see the assembly line how you can actually put a solid electrolyte. You have to do a lot of changes.
Can I just reply to that?
Right.
Well, you can put it in powder and you can make it a lot of kilos and you can even put it on a membrane, which is what we are actually doing
that also needs some changes, which are quite significant. See, I tell you, most of the companies and all, they have roll coaters and, having a powder. And the important thing is, that should also should take into account the electrode content, because industry wants a very high electrode, per square centimeter area. So with the way the solid electrolyte is going to come, they've also predicted that solid electrolyte should go onto the electrode system, right? So that's a lot of engineering. It's not an easy engineering to achieve.
Yes, but
I know this. We also work on some electrolytes. Things like LL0 and a lot of Macedon structures. Actually engineering them onto the electrode is a tough ask. I know many people are giving some solutions, but if you really want to have a very high loading of the active material, and you also want to have a good contact, that's quite a challenging system.
maybe the solution will be in the middle, having the polymerized binder.
So again, also with a positive time, we also have this strategy where we are actually having a polymer as a pusher between. That is also a strategy that I think many of the national labs in the US have done, especially Nancy Duffy and all these people have done it. So that's another strategy. But what we are telling is the final one will be probably a mixture of things. Because the mechanical strength, is very difficult to achieve with just a polymer, especially the dendrite penetration tests and things like that. So there you will have, but that design is also not that easy. The easiest part is, you can actually have it as a rose. That's the biggest advantage with kind of soft, or semi-soft, or composite soft systems, which is probably not so easy with the solid electrolyte system. Because you must be aware more than I am. This has been there since 1950s in the international labs. Okay.
Depends on the solid electrolyte.
The structures are pretty much the same. They're not changing the crystal structure. Crystal structures are the same. All we have done is tweaking with, having a bit more titanium or having something. But at the end of the day, when you're actually going to put in a practical cell, there are severe challenges. So I think this will take some time to solve. Because you have just the other day I saw some Google news. Chinese have a 1,000-kilometer car with single charge with a solid. I don't know. Yeah, as you know, there is a scam. I hope you are aware. Many of the Chinese batteries, which come as labeled as sodium ion, they're actually repackaged as lithium ion batteries. One has to be very careful. So in China claims that we already have the sodium ion. Actually, it's not true. Otherwise, if you have flooded the market, everyone wants to buy cheap products, and China is the best option. We have a budget. We can discuss. I need a cup of coffee.